Hi there. My name is Caroline Famiglietti. I am a PhD student at Stanford, and my project tries to understand the effects of different model parameterization assumptions on the prediction of net biome exchange, which is a really critical variable for understanding the future of terrestrial ecosystems amid a changing climate. So NBE, net biome exchange, essentially represents the balance of carbon fluxes entering and exiting an ecosystem. But what's really important and presents kind of a problem for researchers like me is that future predictions of NBE are really uncertain, and they tend to diverge extremely wildly between different models, as you can see in this plot at the right. So every line here is a different model, and you can see that these predictions by the end of the century range from really large positive values to negative values as well. And it turns out that a lot of that uncertainty comes from basically choices in how we assign model parameters or kind of coefficients, something like the lifespan of a leaf. How are we going to go about setting that parameter in a global context when there's so much variability from ecosystem to ecosystem, from species to species, and so on? So of course, if we want to have a kind of computationally tractable way of doing this, we need to make some assumptions. But that means that any assumption that we make will inevitably affect the accuracy of the model. So that's where my work comes in. I seek to ask how the specific choice of our model parameterization assumption affects our NBE prediction errors. And what I've done is taken kind of a simulation approach in a fully simulated, controlled environment, simulating first the most common parameterization assumption employed in almost all terrestrial biosphere models today, called the plant functional type or PFT approach. This approach assumes that places with similar vegetation all have the same model parameters. You can imagine that would be kind of unrealistic. Secondly, we simulate a novel, flexible approach called environmental filtering, which we simulate in a machine learning framework. The hypothesis here is that a pixel's parameters can be predicted as a function of kind of local soil, climate, and canopy properties, inherently yielding more spatial variability across the globe than the PFT approach. And we compare NBE predictions from both of those first two approaches to an optimization approach. So we use a Bayesian model data fusion framework that lets us back out optimal parameters for our ecosystem model at every pixel across the globe. And so we're able to benchmark our PFT and EF approaches with those optimal NBE retrievals. Essentially, the good thing here is that allows us to isolate the effects of parametric uncertainty from other types of uncertainties like forcing data uncertainty or structural uncertainties. And what we end up with is a bunch of time series, NBE time series like this at every pixel across the globe. What we want to do is see which of our parameterization assumptions tends to perform better. What we see is that the EF approach outperforms the PFT approach at twice as many pixels as the converse. That's what you're seeing with all of these blue pixels across the globe here. That means the EF approach better matched the optimal NBE predictions for the period 2000 to 2015. And we also looked at a bunch of different other dimensions of this kind of NBE performance, things like the mean across the time series, the interannual variability, and we did see that the EF approach tends to come out on top more often than not. So what this suggests is that there is a large potential for kind of trait-based PFT-free alternatives to parameterizing a terrestrial biosphere model that kind of go beyond the traditional paradigm of assuming uniformity from place to place. And so our work, we think, can kind of inform the development and generation of kind of the next versions of our terrestrial biosphere models, and suggesting that trait variability is a really critical piece for that. I'm happy to discuss more with anyone, so just reach out. Thank you.